Thanks to everyone, in particular to Matteo, to Amira, to Tommaso, for this invitation, and to the whole AI models team. I'm delighted to be in a room with so many known but also yet to know colleagues. So as I said, the slides are online, so you can find them in my website. Being entirely committed, being entirely committed to the critical philosophy tradition, I'd like to start with a question that has been haunting me after a few years of doing research in computer science at the heart of the neural machine learning field, which is, why is it so hard to construct a consistent critical perspective on AI today? I know there has been a lot of excellent critical work in the past few years, and a surprising amount of the authors of that work are today here in this room. But the massive amount of that work is externalist, meaning that it focuses on the cultural, historical, social, economic, and political conditions and effects of the practices and discourses associated with AI. However, from a more internalist or intrinsic perspective, that is, from the perspective of the epistemological and scientific grounds of the knowledge produced by those practices and based on which those practices claim their own validity, critical perspectives have not only been scarce, but also poor at best. And as everyone here knows, the main reference coming from within the field in this sense is the one known as the stochastic parts position from Bender and Kohler, Gebru, and others. And symptomatically, alternative critical perspectives have found it difficult to articulate a coherent critical image of the knowledge produced from within the field. Now, to avoid entering into the details, I would just point to the words of Kirschenbaum and Underwood to give an idea of what the problem is. And I don't have the time to read the quotes, but the bottom line is that we are in a situation where not only intrinsic critical perspectives like stochastic parts are poor, but the rich critical sources that one could hope to mobilize in this context, like Foucault, as Underwood said, seems to be impotent for critical discourse to do anything else than to embrace those disarmingly poor positions. So the question remains, why is it so difficult to challenge AI in its own theoretical territory? And there are, of course, many answers to these questions, and not the least the fact that the epistemological territory, casually referred to as the one of intelligence, is itself disarmingly ill-defined. To the extent that one could be tempted to claim that there can't be an internalist critique because the field itself has no interior. So all internalist attempt to make an account of the field is ideological. And I'm ready to agree with such perspective if the field in question is that of AI. But if we think of statistical or machine learning, data science, natural language processing, or even computational linguistics, things are a little bit more complicated. So after many years of moving across disciplinary borders, I have become increasingly convinced that an important part of the answer to this question is that the classical version of the critical argumentative matrix is broken in a way that makes it epistemologically ineffective. And to put it bluntly, I would say that most, if not all, of what critical perspectives can say about, say, LLMs can be expected to have little to no bearing on how the knowledge about LLMs is produced from within. At the most, it can have effects on the effects of LLMs and on how they are branded as AI or whatever. Now, instead of blaming everyone for not listening to what we have to say, we critical philosophers, I believe we need a diagnosis of this ineffectiveness of the critical discourse. So if I had to identify what the root of the contemporary critical discourse is, I would say without too much hesitation that that root can be found in Nietzsche's philosophy. And even more precisely, in a very short text by Nietzsche from 1873, entitled On Truth and Lying in a Non-Moral Sense. And I don't want to enter into the details of this text, which I assume is known by most of you. So let me just instruct an absurdly simplified version of the critical argumentative matrix that in my reading stems from this text. So that matrix starts by stating that knowledge depends on language. But the relation between language and the world is essentially arbitrary. So any regularity in language or in knowledge is not natural, but cultural / social / political. And as a consequence, we should resist existing regularities and create new ones. And I know this characterization is brutally oversimplified, and I apologize for that, and it's unfair to the myriad subtleties and alternatives within the contemporary critical tradition. And in particular, you can think of a materialistic version or a materialist version of this matrix where language would be replaced by material conditions, and the second line would claim that material means are contingent and changing over time, they are historical. But model this oversimplification, I think it's possible to claim that some version of this argumentative matrix brought about a radical renewal of the 19th century critical project in Western thought, and became the mold for most critical endeavors in the 20th century, from the Frankfurt School and post-structuralism to neo-pragmatism, critical theory, and cultural studies. Even Wittgenstein's philosophy has been associated with Nietzsche's views as expressed in this very text. In other words, this matrix has been extremely fertile. And in my view, the fecundity relied on its capacity to bring together the epistemological, the political, and the aesthetic domains as aspects of one and the same problem. And in this, it inherited from the three stages of the Kantian critical project, that is the three critiques, right? Critique of pure reason, the critique of practical reason, the critique of judgment. And it is faithful to that project in a very deep way. Now, if I say that this matrix is broken, it is because I think that the necessary connection between the epistemological and the political dimensions, which was crucial for that project, has been suspended. And to say it shortly, the source for that discontinuation is to be found, in my view, in the emergence of formal sciences as an independent foundational region in the epistemological landscape at the turn of the 20th century. Indeed, the new articulation between mathematics and logic, and if you want, computer science, at this time was able to slip through the cracks of criticism and propose a novel epistemology, in particular for a theory of language. I'm thinking here, of course, of work like the work of Carnap, Gödel, Turing, Shannon, Harris, Chomsky, and even the structuralists, all of whom, by mobilizing new formal tools, whether mathematical, logical, or computational, were capable of exhibiting many formal aspects of language, suggesting in various ways that language is removed from the arbitrary actions of socially determined processes. And in this way, the appeal to formal sciences resulted in the construction of an epistemology of language upon non-critical basis in the form of a naturalization of linguistic phenomena. And it is this naturalization that seems to me to be more active than ever in the scientific field of AI, resisting against any critical alternative, which is therefore pushed outside the field in the form of, for instance, ethics of AI. Now, at the face of this new region in the epistemological landscape occupied by formal sciences since the 50s, I would say, 1950s, the most common strategies from critical positions were to either withdraw from the territory conquered by formal sciences or to conduct a rather dogmatic attack toward the conditions and effects of formalization, and most often both. However, given the drop in efficacy of critical perspectives in the face of epistemological and political challenges of AI in this new century, my feeling is that critical thought needs to change the strategy. And that instead of dogmatically targeting formal sciences from without, critical approaches embrace, explore, and develop formal thought as a critical tool through a new alliance between critical humanities and the formal sciences. In other words, that we develop a critical formalism that invents new formal tools that encourage critical effects at the same time as it denounces dogmatic uses of formalism. And with respect to AI, I believe this can provide two essential tools. First, new epistemological tools countering dogmatic perspectives stemming from within the field. And second, new theoretical tools in line with the resulting epistemology and contributing to the non-dogmatic positive production of knowledge about whatever these models are about. And I think I like to think the two parts of my talk that are going to come as ways of contributing to these two tasks. So, first of all, how can a formal approach to AI and neural language models, more precisely, help us propose critical or a critical characterization of their epistemology? Well, think about this. What kind of entity is an LLM? someone gives you an LLM, what are you given, right? And if instead of making all kinds of epistemological assumptions to characterize neural language models as either brains or agents or stochastic parts or a computer or even models, if you suspend all speculative judgments that are ever so little beyond what you can establish in a positive way and you consider LLMs at their face value, I think that the least you can say is that they are functions. That is some kind of correspondence between arguments and values, or between inputs and outputs, if you want. Now, it's not just an arbitrary function. First of all, it's a function that is at its core explicitly expressed as a composition, and this is how you formally specify a deep neural net. But more importantly for us, it's a computable function. That is to say, a very specific kind of functions, because not all functions are computable. So if you want to produce positive knowledge about this object, you cannot be too wrong if you start by adopting the epistemology that is associated with computable functions. And luckily for us, there's indeed a formal theory of computable functions, so you might as well start from there. And as you certainly know, the theory is that of Turing machines, so you can safely say that your LLM is a Turing machine. But it's useful to know that there is not only one formal theory of computable functions, but actually there are at least 3 of them, namely Turing machines, recursive functions, and lambda calculus. And thanks to the fact that they are formal theories, it is possible to prove that all 3 theories are equivalent in a very precise and strong sense, namely that they all characterize the same set of functions. So let me choose lambda terms as my preferred formal theory of computable functions, if only to avoid any possible slippery slope associated with the name of Turing and his notion of machine and thinking. What is important is that all the 3 characterizations see computable functions as sequences of elementary steps. And in the case of Turing machines, as you certainly know, there are the steps are move to the right, move to the left, right, erase, etc. In the case of lambda calculus, these operations are basically 2, which are lambda abstraction and beta reduction. But you don't really need to know the details of these for the argument that I want to make. It would take just 1.5 minutes to explain this. Not that it's a very complicated thing. There's elementary steps. So that's it. Any computable function is nothing more than a more or less complicated arrangement of those elementary steps. So now we can ask the specific epistemological problem that computable functions raise, namely, how do you know what one of these functions do? So their formal characterization is rather disappointing in this sense, because answering that what they do is to perform a series of elementary steps is certainly missing the point. In other words, we know that these functions compute. We know even how they compute, namely by performing a series of elementary steps. But how can we know what they compute? And this is, to me, the way in which a formal approach to neural models can formulate in a critical way the epistemological question about LLMs. So let me give you an example. Imagine I give you this function. Function is a lambda term, so it's a Turing machine to some degree, but it's also a computable function in the lambda version. It's also a program, if you want. And I claim that for an encoding of natural numbers as the one that I show in the slides, the function P computes addition. How do you know? Well, the first thing that you can do is to apply it to those 2 representations, here the ones corresponding to 2 and 3, evaluate the function, or run the program if you want, or still perform a sequence of beta reductions, and check that the result is indeed the addition of the first 2, here 5. But here's the thing. If I give you this other function and you do the same thing, you find that it also computes addition for 2 and 3. So what can you conclude from this? Would you say that this function also computes addition? Well, you certainly need more evidence, but how much evidence? You might think that you can define a finite set of numbers to test, and you can collect the results, and you might then be able to produce statements such that this, the first function computes addition in 100% of cases, or maybe even 99% of cases, while the second one, say, in only 10%. But what is the threshold about which you can positively establish that a computable function computes addition? If you know what addition is, this question barely makes sense. And if you don't know what addition is, well, it doesn't make sense at all. And this shows that if you adopt a perspective like this, what a function computes is not a property of the function. Everything computes addition to some extent. My coffee machine computes addition, or this stand computes addition, just very poorly. And as you know, a broken watch gives you the right hour twice a day. So even if you require that a function passes a test with 100% accuracy, it is trivial to prove that for any test of this kind, there's an infinite number of functions that pass the test with 100% accuracy and don't compute addition. And the problem is that the only kind of evidence that you can provide in this way is empirical. But what a function computes, provided that this question makes sense, it's not an empirical property. Functions don't happen to compute addition, as a tree happens to be 3 meters tall, or Trump happens to be the president of the US. And addition as something that can be computed by a function is not an empirical object, property, or operation. To compute addition means to compute it for an infinite number of cases, and that infinite number cannot take an empirical form. Now, you might be tempted to say that then we cannot know anything about P. In particular, we cannot know whether the function computes addition, and yet I still claim that the function P computes addition. So maybe you can come up with something else. For instance, you can open the black box and you can try to interpret its inner functioning. After all, we know what a computable function is made of, so the identification of internal patterns of elementary steps might give us some insight of a different kind than the one we had on what the function computes. And indeed, in the case of this simple function, you might be able to understand what the function is doing and why the second one does not compute addition, but always outputs the number 5. But now I claim that this other function, P double prime, also computes addition. How do you know? Are you going to start looking for patterns inside this function to see if something can be interpreted as addition, or change a character here and there and see how it affects the computation over a test set? Good luck with that. Mostly because it is also easy to prove that for any function for which you can establish what it computes, there is an infinite number of other functions that compute just that and are of arbitrary complexity. So the problem here is, again, to think that the computable function is an empirical object itself that should be studied as such by the empirical exploration of its components. So addressing AI models as formal objects allows first to show the shortcomings of this epistemology, and also to reveal how all the metaphors and precarious analogies trying to present these objects as either brains or living organisms or agents or even societies or physical systems might be little more than attempts to hide these shortcomings, not without external consequences, including ideological and political effects. Now, once again, one might be tempted to say that if these objects are not empirical, then nothing can be known about them. But given that we do have a formal theory of computability, addressing AI models as formal objects allows us also to suggest alternative orientations where positive knowledge can be produced about them. And that is the whole point of a formal theory of computability, to be able not only to say or to claim that a function computes addition, or whatever they compute, but to prove that this is the case, as I've been somewhat suggesting so far. So if you think of the computable function as a simple computer program, just another name for it, from a formal point of view, the classic way you would do this, you would achieve something like a proof, or more generally to understand what the program does, as well as to obtain robust results in terms of verification, correction, optimization, and so on, is to view that program as the implementation of an algorithm defined on an abstract structure, which is often the result of a formalization of properties established informally by a theory about a given content. So for example, if your program is an automatic language translator, it would typically be the implementation of an algorithm based on formal grammars for natural language, which themselves result from a formalization of linguistic theories. If you have a calculator, then your structure is, for instance, a mathematics, itself formalizing some mathematical theory. If you have a program that computes the life expectancy from personal data, the formal structure is some model resulting from it, say, resulting from sociology. Now, of course, I'm well aware that the whole point of machine learning is precisely that for some reason one cannot or does not have an explicit formal specification. And this is precisely where the strength of machine learning resides, and in particular of deep learning. And in this case, the informal specification is not given in the form of a theory, but of a much more ambiguous task. And it is not that you don't have any specification, but the specification is given implicitly in the form of data, in a way that the best that you can do is to find a function that performs the task well enough. And the benefits of this procedure don't need to be reminded here, but the key point is that empiricity is a matter of the data, not of the resulting function. So any empirical analysis of the function, of the program itself, completely misses the point. For a computable function, the only legitimate epistemological question is, what is this function the implementation of? Now, does that mean that we're doomed? Well, the whole point of the rest of the talk is to answer no, because a different research orientation is suggested by this analysis, namely, it should be possible to make explicit the specification that is implicitly given in the data in the form of a formal structure. And if that were possible, then unlike current evaluation and interpretability practices in the field, we could use that structure as a formal specification, which can both provide theoretical insights with respect to the under-specified task and formal explanations with respect to the computable function. You can wonder, but then, can that really be done? And in the second half of my talk, I will focus on the formal explainability part of this diagram, and I want to first show you that that has already been done, at least to some extent, and then show you how, together with some colleagues, we are working to push that line of research further, and we can discuss the theoretical interpretability in the Q&A if you want, which to me has to do with structural linguistics, just to announce that. Now, as most of you know, current LLMs are composed of, say, 3 relatively independent programs that are executed sequentially. So first, the text inputs are automatically divided into subwords units and tokens by a tokenization program. Next, each of these units is transformed into a vector in such a way that the resulting vector space is taken to implicitly encode significant linguistic properties of these units. And this was what is usually called embedding. And finally, each of the words in a sentence is combined with all the other words or tokens to produce word vectors that are sensitive to the context of that sentence. And this is done using a mechanism called attention. And I will focus on the embedding mechanism, which to me holds the key of the whole pipeline, and we can discuss why later. And the idea is that once we understand how the embedding space works, tokenization and attention can be understood in relation to that space. So how do you get an embedding function or a program? Well, the usual way in which this is done is known to everyone here, namely, you gather a ton of junk data, and you turn the neural net crank, and then you get this program, right? At the other end of the neural net, you recover an embedding model that is a computable function or a program which outputs a vector for every word or token in the input. As you know, word2vec is the best known of these models. And to make things easier to grasp and avoid the suspicion, but also the mysticism of very high dimensions, in the rest of my talk, I will use a running toy example as a setting where the training data is the English Wikipedia corpus, and the words, or rather the terms, are the 40 most frequent characters in that corpus. So from a strictly formal perspective, there's practically no difference. We can discuss eventually if you're not convinced by that statement. So an embedding model trained on that data will take a character and output a corresponding character embedding, that is a vector representing that character. And if I could zoom there, you would see that in this case, after training by word2vec, by the word2vec algorithm, character embeddings cluster more or less into digits, vowels, and consonants. What is important is that we are here in presence of a clear case of what I have presented right before, which lies at the heart of large language models. And indeed, to understand what embeddings computed in this way do, hundreds of researchers in the field apply the most varied empirical methods, which, however invented, exhibit the shortcomings that I have identified before. So how can we do otherwise? So to start answering this question, I'd like to draw your attention to a fundamental result appeared right after the release of word2vec, so more than 10 years ago, which in my view hasn't received the attention it deserves. In 2014, Levy and Goldberg proved, not by empirical methods, but by a formal analysis of the cost function, that what word2vec was doing is to perform an implicit, low-dimensional factorization of a point-wise mutual information word context matrix. And what is more, they recall that the algebraic technique of singular value decomposition provides an exact solution to this problem. So rather than explaining what each of these terms means, let me show it to you with an example. So take the English Wikipedia corpus, construct the point-wise mutual information matrix, the PMI matrix, which where words are, or rather terms, are just characters, and contexts are pairs of characters, one to the right and one to the left. And all this is something you can do by hand in your computer. And then you perform SVD, which is something you can do with any good old-fashioned numerical library in your computer, NumPy if you want. And this will give you three matrices which, when multiplied together, result in the original matrix. That's what factorization means here. And then multiply the first and the second matrix, truncate the resulting matrix to make it low-dimensional, keeping, say, the three most important vectors, and consider now the rows of that matrix, not the columns, and consider them as three-dimensional embeddings. So when you plot them in three-dimensional space, voila. You see that the initially unstructured set of characters now organizes into clusters of vowels, consonants, digits, and special characters. And of course, what I did here with the characters in Wikipedia is something you can do with words or tokens in a huge corpus up to some computational complexity. So Levy and Goldberg's results say that whatever word2vec and the neural net is doing for embeddings, it will never be anything else than just an approximation to the result of this procedure. So, and they don't claim it, they prove it. You can prove that result. So what can we conclude from this result? Well, first of all, that the surprising properties of embeddings are not to be attributed to the specifically neural character of the model, because non-neural techniques are capable of producing it. But there is much more, because it's possible to prove that those non-neural techniques are the best way to achieve what the neural models want to achieve through their cost function. It doesn't just produce the vectors, but it produces them exactly, which means that any model, whether neural or not, will be nothing but an approximation to this solution, and whatever that model does, it will be determined by the limits of what this algebraic approach characterizes. So to me, this is a first fundamental step toward moving away from the model towards the data and finding principles to characterize its underlying structure that can be mobilized to formally explain the behavioral program as I proposed before. However, this idea has barely been pushed further in the field, and in particular, the authors of these results recognized that they didn't know why this alternative approach worked. And they asked, can we make this intuition more precise? We'd really like to see something more formal. As I said, it's been more than 10 years from these results, and we have hardly seen anything in this direction. So this is where starts the work I'm doing in collaboration with some mathematicians and theoretical computer scientists. And I want to talk to you about that in the last part of my talk. So what would something more formal look like? So take the Wikipedia character context matrix again. We will be passing things from the space of terms to the space of contexts and back. So to make it easier to follow, I have written in red everything that has to do with the space of terms, words or characters, and in blue, everything that has to do with the space of context. Right? Now, a matrix can be interpreted in many ways, but one of those ways, thank you, is that a matrix represents a function or a map from the product of two sets, in this case, x, the set x of characters and the set y of context. So a map from a product of these two sets to the real numbers. In other words, it can be seen as a function that if you give me one character and one context, I give you a number. That's it. That's what that writing means. I'm giving you the point-wise mutual information, that's just a number. Now, if you have such a function, you can reorganize this function for free in two ways. First, I can see it as a function from characters to functions over context. That is, if you give me a character, I give you a function which itself takes context and returns a number. This is what is called carrying in the field, for those who know. Another, you can picture it there as saying that if you give me a character, I give you a row vector. right? Instead of giving me a character and a context and I give you a number, you give me a character and I give you a row vector. That's a function between the context and numbers, right? And symmetrically, I can also see it as a function from contexts to functions over characters. If you give me a context, I give you a column vector, which is itself a function over characters. So here's a diagram of the two functions that I've just created by simple reorganization of the original function. Now, I can also extend linearly the set of characters and embed it in the set of functions over characters, and do the same with the set of contexts. And this operation is not trivial, but you need to trust me in that there's always a way to do this that is consistent and totally generic, meaning that it is purely formal, it's a formal property, not depending on the data. Basically, out of a set, you construct a vector space, which is the free vector space generated by that set. So no information being constructed there, just an empty vector space, if you want. And since these extensions have very nice properties, then the maps that I had before, the ones that were mx and my there, can be lifted to maps between functions over characters and functions over context, and vice versa, which are the ones that are represented with the dashed lines there. And because the target of one of these maps is the source of the other, and the other way around, I can compose those maps and obtain this way two new maps from the respective spaces to themselves, and not to another space. Or in other terms, two operators, one from the set of functions over characters to itself, and one from the set of functions over context to itself. Now, these operators have a lot of structural properties. And in particular, if you're working over the real numbers, you can apply the spectral theorem and obtain a set of special vectors that are called the eigenvectors for each operator, and construct new orthonormal bases for your respective spaces. And these vectors are the ones that constitute the matrices resulting from SVD that I've shown you before. But the key property to retain is that these special vectors or eigenvectors are the linear fixed point of the respective operators. So when you perform SVD on a word context matrix, from a formal perspective, what you're doing is first constructing a covariance matrix of either words, which is what you're seeing there, or context, which I'm not showing, and then taking eigenvectors for those matrices. So what are these eigenvectors? And as I said, they are linear fixed points. In other words, if you see your new matrix, this one, M there, if you see it as a map from the space of functions over characters onto itself, the linear fixed points of that operator are the vectors that when you multiply them by the matrix, you obtain the same vector, or a scaled version of it. So if you apply your operator to your space, you will see that most points will be moved to other places, and this will happen each time you apply the operator. But there are some points that are remaining fixed, or moving along a fixed direction, no matter how many times you apply your operator. Now, I know this is certainly a moment to take a break from the heavy formalism and come back to Nietzsche, because Nietzsche belongs to that category of thinkers that are right even when they are wrong. I remember a professor of mine once included Aristotle in that category, because apparently Aristotle argued that the void couldn't exist, because if it existed, objects with different mass should fall at the same speed. Think of that. So in the same line, in the paper I mentioned before, Nietzsche argued that form cannot be the source of knowledge, because otherwise a deaf person seeing a Chladni plate would know what sound is. Now, if you, like me, didn't know what a Chladni plate is, here's a short demonstration. And granted, if a deaf person seeing one of these wouldn't know everything about sound, the claim that they could not anything about sound because the form we see is completely unrelated to sound seems like an overstatement. Now, however anecdotal, I like this example because one could claim that this form is expressing some of the material dynamics of the phenomena at stake. And mind you, the way that is achieved is precisely thanks to the existence of fixed points of an oscillatory operator over the space defined by the plate. The grains of sand tend to accumulate at the points that remain fixed through the oscillatory operator. Now, just like for the Chladni plates, if you look at those particular points in the case of the operator constructed from data of linguistic context, these points reveal a lot of structure about the space of terms. So first of all, you have an order of importance, which is given by the middle matrix there. So there are vectors there are fixed points that are more important than others. But also, at least in the case of characters, they are highly interpretable. Here you see that the three most important vectors, which are the ones that I plotted before, they show linguistic properties. In particular, the first one distinguishes between digits and letters, the second one between vowels and consonants, and the third one selects special characters. And the same is the case for the context. And similar structural features can be observed when you apply these to words instead of characters. Now, I'm sure all this has been a little bit too quick for those who see it for the first time, but the bottom line is that in the case of classical embeddings, one cannot only replace neural models by well-known algebraic procedures of matrix factorization over a matrix representation of the data, but also explain those models through these techniques. And second, those techniques point to an underlying structure of the data, which a formal analysis of those techniques allows to understand as determined by the fixed points of what I would like to call a distributional operator. And all this is somewhat known, even though, if to the best of my knowledge, the formal structure behind these methods has played little to no epistemological or theoretical role in AI. Now, if one considers the formal structure captured by this linear algebra setting, one can realize that, in fact, it's pretty weak. You have a set of fixed points in the space of functions over terms, which is canonically paired with fixed points on the space of functions over context. And that set of fixed points, or of pairs of fixed points, is ordered. So basically, you have an ordered set. That's it. And from a formal perspective, that's not much. For instance, in the case of characters, you can have a fixed point that distinguishes between digits and letters, as we've seen, another one that distinguishes between vowels and consonants. But out of the formal structure alone, you cannot say that a vowel is a letter. And this limitation is the effect of the choice of linear algebra. But the usage of linear algebra for the analysis of data has practical, sociological, and historical grounds, but not necessarily formal or theoretical grounds. So by characterizing this tool from a purely formal perspective, that is, as determined by the fixed points in a distributional operator, we have given ourselves the means to free ourselves from the specificities of that choice and propose a radical generalization of this setting in a way that is, as far as I know, pretty unknown in the field. And in the last part of my talk, I will present the main ideas of this generalization. And you don't need to know all the details of this categorical generalization. It's enough to know that instead of starting with a matrix, as in the previous case, we will have a generalization of the same idea called a profunctor. And the set of fixed points is called the nucleus. Just retain those two words. It's just the same thing as before, but in a new general setting. And it's not just a set. The set of fixed points is not just a set, but it's a category. So it's a set with more structure. Now, this profunctor functions much in the same way as our matrix before. If you give me an element from the category of terms and another one from the category of context, I give you some measure of their interaction, which in this case is not necessarily going to be a number, but an element of a nice category. And in the generic case, that category is the category of sets. So if you give me a term and a context, I will give you some set, which is not very meaningful. But the key point is that thanks to this general setting, we can change that measure category to something that makes more sense. And by doing this, you're not only changing the measure, but you're changing the structure of the measure. in such a way that you can take advantage of that structure to make appear new and richer structure underlying the data. So let's take a concrete example and enrich our profunctor with the category of Booleans. In other words, for every pair of a term of and a context that you give me, I'm going to give you a 0 or a 1. It's kind of a simpler case than before. Now, I can construct my operators in a way analogous to the linear algebra case. And we want to look at the nucleus of this adjunction. That's a technical term. But basically, it's the same square that I've shown you before. The nucleus of these operators. And that is the set, or rather the category of all the fixed points. And if you remember the case of the linear algebra, where we were looking for vectors that remain unchanged up to multiplicative constant through multiplication by a matrix, you can picture the new setting as a binary or discretized version of that matrix, where the coefficients are either 0 or 1, and we are looking for binary vectors that remain unchanged by some sort of multiplication by that matrix. But binary vectors can be seen as subsets, containing only those elements that are marked with 1, right? Not only vectors, you can see them as subsets. All things that have 1 there, it's a subset of all the set. So let me show you what the actual subsets that correspond to the fixed points are in this case. And each of these fixed points is a set, and sets, unlike vectors, can be included into each other, opening the way to a much richer structure. So you can see this richer structure if we organize those sets following their inclusion properties or inclusion relations into the corresponding lattices, representing a partial order over the nucleus. And the same is true for the space of context, which is in strict duality with the space of terms, such that you have a one-to-one pairing of these lattices. So even if by discretizing our original matrix, it looked as if we were moving towards a poorer framework, under this very simple case of our categorically generalized setting, a lot of new structure becomes available to us. Now, we did lose something by using a binary measure instead of a real one or a continuous one. So in the end, we would like to have the best of both worlds. And to do that, instead of enriching our profunctor over the Booleans, we can enrich it over the extended real. So here again, if you give me a term and a context, I give you a real number. But these are not exactly the real numbers that you know. In particular, addition and multiplication work in a funny way. But what is important is that we're again here in this Chladni figure situation, in which you have all the points in your space, and after the action of the operator, most of them are displaced, but a bunch of them remain at the same place. So if we take our toy example of characters in Wikipedia, which is something like this, and a more precise representation of the nucleus on the left is the following one, where you should think of all the points within these boundaries as points included in the nucleus. And although I have no time here to explain the details, you should already see that the nucleus is endowed with a rich geometric and algebraic structure. And there's a dynamic version of this you can find online. I can show you during the Q&A. But one last important remark before finishing, which is that thanks to the highly principled construction, it is possible to formally prove that each element of the nucleus, in this case, can also be seen as a computational type in a strong sense, defined within the framework of linear logic, which means that the structure of the nucleus can give birth to an emergent logic by which linguistic properties could receive a symbolic representation. And finally, from this characterization of the embedding space, other components of the LLMs can be studied as specific aspects of this structure. So I don't think there's much time to conclude. I mean, 45 minutes exactly. So maybe I stop here, showing my nice collaborators, and we can discuss about the conclusions in the Q&A. Thank you very much.